Okay. We proceed with ZP theorem. Yesterday we learned general setting and real Z, whole numbers. Well, today we will learn what happening in ZP. Well, in whole numbers we had a lower bound, right? And the structure theorem about what happening if lower bound is attained. Well, similarly, I'll state at least prove. I'll prove lower bound for ZP and state the theorem about situation structure of sets for which lower bound is attained. But well, it's long theorem. I think we don't have enough time to finish the proof. We start proving the theorem. Okay. First, lemma. Lemma 1. What is this? It's a if AB subset of G finite are finite non-empty subsets of abelian group, finite abelian group of a final abelian group G and cardinality of A equals cardinality of B is strictly greater than cardinality of G. Then A plus B is G. Strictly greater or equal. Can it be equal? Well, no, it can't. Well, proof. Finite. Yes, sorry. Finite. Sorry. Finite abelian group. Sure. Otherwise, this doesn't make any sense. Right. Finite, everything finite, A, B, and G also. Well, fix any element. Let's fix any element E from G. What can we say? We can say that we can state that E minus E and B are intersecting. Why? They must intersect. Why? Because it would be what?
Since we have to prove that
Yeah, from this follows that A plus B equals to G. But why this? Well, this is true. Because they are too large to be non-intersecting. They don't fit inside the group if they are non-intersecting. Since otherwise, if A plus B, if E minus A and B non-intersecting, then cardinality of G is at most cardinality of E minus A union B, right? Because E minus A union B is a subset of G. But this is A plus B, cardinality of A plus cardinality of B, if they are non-intersecting. But this is strictly greater than G. Contradiction. Well, they intersect. So there exists A from A, and there exists B from B, such that E minus A equals to B, right? So this means that E equals to A plus B belongs to A plus B. Since this is true for any element E, so this means that A plus B equals to G. So, as you see, if we state that A plus B equals to G, there are no structure. If sets are large, there are no structure. For finite groups, there is common difficulty. Any two arbitrarily large sets in cardinality have the property that A plus B equals to G. So, when we learn some structure of small subsets, we have to exclude the case when we have equal cardinality of some set equals to ZP, right? Because in this case there are no structure. It's not structured case. Okay. Well, lower bound, Theorem 1. I'll state it. After statement, we need some lemmas, some number of lemmas. This is Coshy-Davenport theorem. Well, as you know, well, this is kind of 19th century theorem. This is not a result of joint paper, right? This is a result. Cauchy published. Well, we don't know if this Cauchy or someone else. Well, Cauchy was director of French Science Academy, and there was a tradition in French Science Academy sign the right name of the director under all the publications. So we don't know real author of this paper. Probably it was someone else. Well, but Cauchy published, and everyone noticed that, because in the 19th century language says was French. Davenport print this paper before Cauchy in English, but no one can read that, so it wasn't noticed, and noticed by historians who found that publication and found that it was before publication of Cauchy, and so it's historical construct. Coshy-Davenport actually they found this theorem independently, and probably Davenport was first one. Okay. Coshy-Davenport theorem says if and A and B subset of ZP non-empty subsets and then that's all. Then cardinality of A plus B is at least minimum between A plus B minus 1 and P. This is Coshy-Davenport theorem. Okay, how to prove it? In order to prove that, we need to prove one lemma. Definition. For a pair of subsets, AB subset of ZP and for any element E from A plus B, we define E transform of the pair A and B, AE and BE, AE and BE, where AE is A union B minus E minus C minus C minus C 1 minute. A minus B, I suppose. A minus B. B minus E. B plus E. B plus C. BE would be B intersect A minus E. Yeah. Now that's correct. Well, this is new pair AE, B. For AB, we define E transform of the pair. There are two proofs of the Coshy-Davenport theorem that I know. This is, I think, less complicated than the second one. This is just because, well, probably, well, for first proof we need null sets actually. For this one we need groups and E transforms, that's all. Well, do you understand the definition? Well, why we take E from A minus B? We can define AEB for any E from the P, but we restrict only to A minus B. Why?
So we can intercept.
Yeah, because we want B to be non-empty. If E not in A minus B, then B is empty set. We want to transform a pair of non-empty sets onto pair of other non-empty sets. If we take other E, this is not true. Okay, properties of a transform. First, A always subset of E. Right? Second, B is always subset of B. Right? Third, well, it's first. Second, if A, B non-empty, subsets, then AE, B also non-empty subsets. Also non-empty. Well, next. AE in cardinality A plus B always as cardinality A plus B. A plus cardinality of A plus cardinality of B. Oh, no, sorry. In this statement. AE, cardinality of AE plus cardinality of B is cardinality of A plus cardinality of B. Right. So fourth, AE plus B is set always subset of A plus B. That's all we know. Actually, this is all we need. Right. Let's prove. Well, first, is it clear? The first, because, well, by construction, this set always contains A. This set always subset of B because its intersection B with something. Right. Proof. Second, how to show that E and BE also non-empty. Well, we have to find some elements inside AE and B. What element we can find in AE? A subset of AE. So this means that AE non-empty because A is non-empty, right? What about B? Can you show me at least one element which contains B? Always contains. Just use this one. Yeah. There exists A from A. There exists B from B, such that E equals to A minus B. Right? So, B, what element always contains? Can you just say what elements is lying inside? What element lying inside B? Always lying inside B. Minus. It's minus. It's B. B always inside B. Why? Then B in B always. Why? Since B is inside B, right? Yeah, and in order to show that some element belongs to intersection, we have to show that this element belongs to both sets. Right, second set. Why B is in A minus C? Why? Why B is in A minus E? B equals to A minus C, right? Right? So this belongs to A minus C. So B belongs B, B belongs A minus C, so B belongs B. Directly what? Okay.
Substitute A minus B over there in place of A. Can't we do that?
We can, yeah, we can, but well, we want to have the, we construct this E transform in this way, this property holds. So that's why we intersect B with something. Yeah, we can do this actually. B plus E intersect A. This set has the same cardinality, but well, it's not a subset of B usually, right? So we can shift this this construction, but we wanted to have these properties. That's why we made it this way. All right. So B is inside B, so B is non-empty. At least one element always in B. All right. Next. third. Well, AE plus B cardinality of A plus cardinality of B is cardinality of A union B plus E plus A plus B intersects A minus E. By inclusion exclusion formula, we have this union is cardinality of A plus cardinality of B plus E, so which is cardinality of B, right? Minus cardinality of intersection. And this is cardinality of B. Well, look, we can write that it's in cardinality, the same as B plus E intersect A. Because this set and this set are actually shift of each other, right? Look, this set is this set minus C. Right? Do you understand? We just extract E from both parts. How to shift that the intersection? You shift both components. So that's why cardinality of the intersection, this intersection and this intersection is the same, because they are not equal as sets, but they are shift of each other by one element. Well, so this is A intersect B plus C. So they cancel each other, and it's A plus B. Okay. Fourth. How to show that A plus B is always subset of A plus B? Just take any element, A1 from AE, B1 from BE, and we have to show that their sum always belongs to A plus B, right? Well, this first part is union. AE is union, right? So it means that either A1 belongs to A, or A1 belongs to what? B plus C. Well, B1 belongs to B and A minus C together. Well, so if A1 belongs to A, then B1 belongs to B, right? Yes, E always subset of B. Right. And A1 plus B1 belongs to A plus B. If A1 belongs to B minus B plus E, right? B plus E. Then B1 belongs to A minus C, right? Because BE subset of A minus C. And E1 plus B1 belongs to A B plus E minus plus A minus E, and this means it belongs to A plus B. That's all. Okay, here's 4 properties of a transform. Let's prove Coshy-Davenport theorem. Well, I have to write this definition. Well, we use induction. Let's proceed. By induction, on cardinality of B. If cardinality base of induction, if cardinality of B is 1, then what? Then A plus B is what? Yeah, because it's shift of A, right, by 1 element. It's cardinality of A. Well, which is cardinality of A plus B minus 1? Exactly. Right? And everything is proved. Well, in this case, naturally, A plus B minus 1 smaller than P, smaller than P, because A is subset of ZP. Right. Okay. Transform. Well, now, suppose that theorem is proved for some cardinality of B, right? Some cardinality of B or smaller. I don't want to denote this cardinality by some K or something. we don't need it actually. Some cardinality of B and smaller sets B. Well, then how to make this step, inductive step? How to make this? Well, we need this E transform. Look, BE is always subset of B. So B could be smaller than B, right? On the other hand, A plus B also a set of F plus B. So we just do this. A plus B. Take any. Let's take any. Let's take any E from A minus B and consider A plus B is at least, at most, AE plus B in cardinality. By the way, forgot to mention. And if BE in cardinality strictly smaller than B, then by induction hypothesis, we have this. A plus B is at most AE plus B. By induction hypothesis, B is smaller than B, strictly smaller than B. So we can use induction hypothesis for A and B, right? So this gives us, this is at least minimum between AE plus cardinality of B minus 1 and P, right? Well, but AE plus cardinality of A plus cardinality of B is cardinality of A plus A plus B. That's all.
And the first step, we are using property 4.
We use E transform simply. If it works in this case.
Yeah, but I mean, say that A plus B, the cardinality of A plus B is bigger or equal to the cardinality of A plus B, and we are using.
We're using force property. Force property, right? It falls from force property. Well, if we reduce B in cardinality by E transform, then we showed everything by induction. Okay, what if we don't reduce B? What would we do? What we do if we don't reduce cardinality of B? We can take another E and try this E. If we reduce, then we proved, right? We don't care about what E we take. If this holds, then everything K, right? But if BE equals to B, see? B is subset of B, always subset of B. So if B equals to B for any A, if from A minus B, this set is not covered yet, right? This case is not covered. We cover all the cases if we can reduce by taking some element of A minus B. Okay. Right. If for any E from A minus B, BE equals to B, then what? Then B intersect A minus E, E minus E, right, A minus E. E is equals to B for any E, right? When this happens, when such things happen. It's subset of B. A for any E from A minus B.
Here are some results.
A minus C is subset of B. No. Converse. B subset of A minus C. B subset of A minus C. Right. Let's transform this a bit. This is equivalent to A for any E from A minus B. B plus E is subset of A, right? But this is true for any E. But when this holds? This holds for only when a B minus B plus A is subset of A, right? Right? Well, this thing contains 0. So A is also subset of this thing, right? So these sets are equal. When they are equal. Remember the structure theorem? When they are equal. And we didn't prove it yet. Yeah, it's true, but we didn't prove it. When this sets are equal. We had the structure theorem, remember? When there are subgroup, right? When there are subgroup, if and only if there exists subgroup H of the P such that in this case B minus B is subset of subgroup, right? Not coset. In the structure theorem, B minus B must be coset, but it's in here we have not cardinality of equality of cardinalities, but cardinality of sets. So in this case, B minus B must be subset of subgroup. And A is a union of cosets of H. Right? Well, well. What kind of subgroups we have in ZP? By addition, naturally. Zero and ZP, there are no other subgroups because it's this cardinality of ZP is prime, right? Cardinality of subgroup is divisible by cardinality of a group. In P has no other divisor than 1 and P, so there are no other subgroups. Well, okay. There are no other subgroups, so either H is 0 or H is ZP. If H is 0, then B has cardinality 1, right? And everything is good. And theorem is proved. If H is ZP, then A is ZP. Then A is ZP. Because it's union of cosets. There are the only one coset of this group. And B is subset of ZP. Well, what can we say about this case? And well, A plus B is P, right? It's, and A plus B minus 1 is at least B, right? So everything also showed, because minimum of A plus B minus 1 and P attained on P, and everything is good. Well, theorem is proved. See, why in the P everything this theorem is quite proof of the theorem quite lengthy, right? Why? Because, well, in the whole numbers, it's a short proof, easy theorem. This is because in the whole numbers there are addition operation which is well this operation not simple operation but operation with property that if A strict is smaller than B and C strict is smaller than D, then A plus B strict is smaller than C plus D. So this is correlated with this order correlated with operation of summation, right? We cannot introduce such order in the P, which would be correlated with addition inside this group. There are overlaps in the operation, and this overlaps doesn't allow us to introduce this correlation between ordering and summation. That's why we have to use something else. The argumentation in whole numbers is not working, and we have to use something else. Well, in this case, we have to introduce the transforms. Good. Well, structure theorem. How do you think? What is structure of A and B if this lower bound is attained? Well, it's well, by first, if A plus B is ZP, then there are no structure. I showed this, I proved this lemma 1 for you, which showing there are no structure in this case. Because this is true for any two sufficiently large subsets. Well, so let's exclude that case. Let's exclude that case. Right. Definition. The pair A and B is called critical. If A plus B is not ZP, we're excluding this case, non-structured case, and A plus B in cardinality is A plus B minus 1, a pair subset of subsets of ZP. So let's classify all the critical pairs. Well, it's Vosper theorem, Theorem 2. We start proving this theorem today and finish, I think, next lecture. We have to show, in order to prove the theorem, we have to prove first the chain of lemmas. Theorem 2. If A, B, subset of the P, non-empty, subsets, and AB is a critical pair, Let's take AB. A subset, such that AB is a critical pair. Then, well, let's take AB to be non-empty subsets. I can state it this correct form. Then AB is a critical pair if and only if one of three cases holds. One of three cases. Holds. First case, it's minimum of cardinality of A and B is 1. Quite obvious case, right? Second case, not that obvious. It's subcritical pair, what I call subcritical pair. Pair is subcritical when we have property that cardinality of A plus B is P minus 1. Not ZP, but P minus 1, almost everything. There exists C from A plus B, B minus B. No. Simply from ZP. Such that A is any set cardinality of A is between 1 and P, simply P, or smaller equal than P minus 1, naturally, because we take A equals to B, cardinality of A equals to be equal P, then the pair is not critical, right? Because of this. Okay. Exists C, A is any set, and B is a subset of no, not subset, I think, right? Yeah, not subset, equal. C minus A complement. This kind of pair. Well, this is structure, well, quite weak structure on my, in my point of view, because A is any set, but B is defined. When we fix A, B is also fixed. Right. And the third case, A is K, cardinality of A is K, cardinality of B is L. Then cardinality of A plus B must be minimum between K and L is at least 2, and also K plus L minus 1 is at most P minus 2. So K minus L is at most P minus 1. then, well, this is restrictions. Well, I just want to make these three cases non-intersecting, to be non-intersecting to each other. Well, let's do this way. Right. What structure? Yes, two sets. We fix cardinality of the sets. What structure? And B are arithmetic progressions with the same difference. Are arithmetic progressions. With the same difference. Well, there are only three cases. In Vosper's theorem, this theorem 2 is by Vosper. Well, there are two directions, right? If we know the hard direction, we know the pair is critical. We have to show that only three cases. There are only three cases when this pair is critical. But we know in the beginning that only the pair is critical. Second direction, opposite one. We know the three cases. We have to show that pair is critical. This easy direction. Well, let's prove first the theorem in easy direction. Then start proving in hard direction. Okay. Well, suppose we have pair of set, pair AB satisfying one of one, two, three. Well, we have to show that this pair is critical. If in the first case, minimum between A and B, we know that minimum between A and B is 1. Well, how to show that the pair is critical? Well, in this case, A plus B, well, suppose, without loss of generation, we suppose that cardinality of A is 1, well, then cardinality of A plus B is cardinality of B, right? And it's equals to A plus B minus 1, and the pair is critical. All right. Well, we have to denote A and B both not equal to ZP. Right. Second case. There exists C in ZP such that here is given coordinate is between 2 and P1, P minus 1, and B is complement of C minus A. Right. If B is complement of C minus A, then C is not in A plus B. Right? Why? C is not in A plus B. Why? Just consider A plus B, right? If C belongs to A plus B, otherwise, if C belongs to A plus B, then what? Then B must be what? B is non-intersecting with C minus A, right? If C belongs to A plus B, then C minus A is intersecting with B. But by condition of lemma, by condition, B is not intersecting with C minus A. Contradiction. Right. So C doesn't belong to A plus B, so A plus B at most, P minus 1. At least one element doesn't belong to A plus B. We have to show that there are only one element doesn't belong to A plus B. How to do it? Well, by Coshy-Davenport, A plus B is at least minimum between A plus B minus 1 and P. Right. A, we don't know coordinate of A, but we know coordinate of B. What the coordinate of B? Its complement. What the coordinate of B? P minus coordinate of A, right? So it's minimum between coordinate of A plus P minus coordinate of A minus 1 and P. So it's P minus 1, lower bound also P minus 1. So upper bound is p minus 1, lower bound, so this means that a plus b is cardinality p minus 1. Which is equals to a cardinality of a plus cardinality of b minus 1, so pair is critical. Well, third case. Third case. Well, minimum between k and L is at least 2. K plus L minus 1 is at most p minus 2. And also we know that A and B both arithmetic progressions with the same difference. So A is A0 plus ID when I goes from 0 till k minus 1. B, this is also progression, so it's B0 plus ID when I goes from 0 till L minus 1. Right? Well, we know K and L both minimum. Yeah, both greater or equal than 2. And K plus L minus 1 is at most p minus 2. Okay. Then what is A plus B? What is A plus B? This is A0 plus B0 plus ID whenever I goes from what? 2, 0, 2, K plus L minus 2, right? Well. Since K plus L is at most p minus 1, there are no overlaps in this set, right? All this kind of representation inside this set are unique, right? Is unique. So this set has exactly K plus L minus 1 elements. Right? This set has exactly K plus L minus 1 elements because it's equal to number of indices, right, inside the set. So A plus B is in cardinality K plus L minus 1. There are, but we used this condition because we have to ensure that there are no overlaps in this ID. So if I goes after, if I equals to P or larger, then we create overlaps, and we create second representation for some element. There are no second representations for any element. So this representation in this case is unique. Okay, so this is A plus B, cardinality of A plus cardinality of B minus 1, and this K plus L minus 1 is at most P minus 2, so this pair is critical. This pair is critical in all the cases. pair AB is critical. We had to show that there are no other critical pairs, and this is kind of difficult. Well, suppose, well, this is in this proof in hard direction. This is easy direction. Now suppose that pair AB is critical. Right. Okay. All we know is that pair B is critical. We have to deduce these three cases. Well, first suppose that A minimum between A and B, cardinality of A and B, is 1. Then we got the first case, right? Then we have the first case. First one. Suppose that minimum between A and B, cardinality of A and cardinality of B, is at least 2 from now. Well, and cardinality of A plus B equals to P minus 1. We have to show that we have this case. We know that pair is critical. I remind you. We know this and this. How to show that we have this case? Well, first of all, there are unique element which doesn't belong to A plus B. So then there are unique C, such that from ZP, such that C doesn't belong to A plus B. Good. Well, what we do next? Next, this means that C minus A and B are non-intersecting, right? This means that C minus A and B non-intersecting. Well, next, this means that B is subset of C minus A complement. Now, we have to use that the pair is critical, right? Well, look. Well, how to use this? A plus B in cardinality is cardinality of A plus cardinality of B minus 1. But cardinality of B is at most what? P minus A, right? Is at most P minus A. That's all we know. Right. So this means that it's at most, it's P minus 1. First, we know that. Second, we know that the pair is critical, so this also holds. So let's use upper bound for B. This is P minus 1. Upper, lower bound are the same. So this means that cardinality of B equals to P minus A. So this means that B is equals to C minus A complement. And we have the second case, right? And we have the second case. Right. Well, now we have these three suppositions. Suppose that minimum between A and B is at least 2. Second, A plus B, which is A cardinality of A plus B minus 1, is at most P minus 2, in order to separate the second case, right? And pair AB is critical. That's all we know. You don't see? What do you see? What you don't see?
It's a bit long. Not too flat. Yeah, it's okay now.
Что там у вас?
That's okay.
Yeah, okay. And pair AB is critical. That's all we know. We have to prove, we have to deduce from these three suppositions. Third case, the structure of arithmetic progression. That's the most difficult part of the proof. So we make it next lecture. Okay, then let's finish for today.